And yeah, this talk is entitled Audio AI for Healthcare Robotics. And so my colleagues and I are going to be presenting on some of the research we've been doing. But I thought I would start by giving a bit of a background into our lab. So we're a cognitive neuroscience lab at the CCBN down at the University of Lethbridge. And some of our lab's research areas are the neural mechanisms of attention, disorders of attention, and so we study ADHD and gambling, and also sensory and perceptual systems. And recently we've done a lot of research on auditory perception. So studying how people perceive speech and sound. And there's a couple of facilities we use to do this research. So we have a 128 channel EEG system to record neural activity. And we also have a multi-speaker auditory presentation room. So that's shown in the photo here. And basically how it works is we have a bunch of speakers that we can use to render sound anywhere in 3D space. And so this is how we do lots of our research into studying how people perceive speech and sound. But you might be wondering what our lab is doing as part of the Autonomous Systems Initiative, as U of L doesn't even have an engineering school, and this is kind of more in the neuroscience side of things. And a lot of this actually arose around 7 years ago when our lab started a collaboration with the Italian Institute of Technology. And this collaboration was with a humanoid robot called the iCub. So that's the robot shown on the right there. And when Dr. Tada went to IIT, one of the first things he realized is that the iCub had a lot of functionality for vision and even tactile sense. So like all the fabric on the iCub there is different tactile sensors, but it had hardly any functionality for auditory awareness. And that just so happens to be a huge area of our lab's research. And so our lab developed an initial auditory awareness system for the iCub. And so in Lethbridge, we have just the head of the iCub, which is shown on the left. Because we're a neuroscience lab, we don't need the full body, we just needed the robot's head. And so our research has always been sort of inspired by the brain. So this initial auditory attention system was inspired by how the brain localizes where sounds are coming from. And throughout all this research, one of the main takeaways that our lab has realized is that speech is a really natural mode of interaction. So I have a quote here from Donald A. Norman talking about how it's the duty of machines and those who design them to understand people, rather than it being the other way around, where people have to learn the arbitrary, meaningless dictates of machines. And I'm going to make the argument that machine learning has really enabled accurate speech recognition to the point that we can really develop intuitive interfaces for people that are going to really increase their ability to learn how to interact with machines and also sort of increase the effectiveness of how these machines work. And I think specifically speech and auditory awareness is really going to enable robots to better understand people and what their intentions are and how to interact with them. That being said, human-robot interactions face unique challenges during these speech interactions. And so after going into this initial robotics research, our lab has really realized that healthcare robotics is actually one of the first industries that is poised to gain lots of these benefits. So last year at ASI, I presented a poster on using speech control for an assistive robot that's shown in the bottom left. And later on, you're going to be hearing from Sylvain and Chris, two guys from our lab, who are going to be talking about speech control for a robot that does deliveries in high-risk scenarios. So having robots that can do deliveries and prevent the spread of COVID in hospitals and healthcare facilities are really useful, and using speech control is a way to control these devices from a distance. And also using speech interaction as another means for controlling rehabilitative robotics. But I thought I'd start off by sharing some of the research I did during my master's thesis. And this is into a type of neural network I developed called a binaural speaker isolation network. And these are networks that can isolate what a target talker is saying in noisy environments. So as a little bit of a background and motivation, as I previously mentioned, speech is a natural mode of communication for humans talking to other humans. And so it follows that it would be very useful for robots to be able to understand what people are saying. But there are some technical problems that robots are facing before this is possible. And one of these problems is what we call in neuroscience the cocktail party problem. And it's the problem of how you understand what a target talker is saying in noisy environments that contain multiple distracting talkers and lots of other noise. And we don't fully understand how the brain solved this problem, but one of the things we know is that the brain makes use of binaural hearing. So basically how this works is the brain is comparing the signal at each ear, and based on those differences, it's making a map of space to figure out where sounds are coming from spatially. Similar to how the brain compares the input from the two eyes to figure out stereo depth, to figure out how far away things are. The brain's making this map of space in the auditory domain. And through that, the brain can attend to a target talker coming from a certain spatial angle while ignoring sound that are coming from other angles. So in my research, I took inspiration from this to develop a neural network architecture that can learn in a similar way. So on the left, we see the ascending auditory pathway. And one of the first things that happens is input to each ear is broken down by frequency in the basilar membrane. And from there, multiple Bushy cells in the cochlear nucleus combine inputs from these multiple hair cells along the basilar membrane. And then it gets propagated up to the superior olivary complex where that comparison between the two ears happens. So I developed a neural network that is learning in a similar way. So it has input from a left and right auditory channel and a couple of initial layers that combine multiple inputs from those channels. And then that gets merged together into a higher level network that is learning to output the target talker's audio. So the input to the network is audio with multiple talkers, and then the output is the target talker's speech. So how I train this network is I rendered a bunch of audio using what's called a head-related transfer function. So this transfer function enables you to render audio as if it was being recorded from inside the two ears. So I created a data set where the target talker is straight ahead at 0 degrees and distracting talkers are off to the left and right. And so this network learned to output the target talker speech while ignoring the distracting talkers. And for evaluation, I tested it out with a system that had 0 to 6 distracting talkers as input. And then I had my network output the target talker speech, and then I fed that speech through a speech recognition network to convert that into recognized text. And so I evaluated this system in a couple different ways. So on the right, we see the speech recognition systems architecture. And that's what's taking the audio as input and outputting text. And so I used a metric called the word error rate, which is basically a calculation of how many errors the speech recognition made when it was recognizing what was said. You can think of it as a word level edit distance divided by the number of words in the target transcript. And another metric I used was the source to distortion ratio improvement. This is a commonly used metric for these networks that are isolating a target talker speech. And because we're a neuroscience lab, and this was an approach inspired by the brain, I wanted to see how well my system performed compared to human participants. So I ran 8 human participants on the exact same data that I gave to my network. I played it through headphones, and the participants typed what they heard the target talker saying. And in this test data set, there is an increasing distractor set size. So as I increased the number of distractors, I tested how much detrimentally it affected the recognition rate using the word error rate. And so here are the results from the experiment. So in green, we have the human participant results. And the x-axis is the increasing number of distractors. And then on the y-axis, we have the word error rate. And the blue line is the binaural network. So you'll notice that they have very similar performance. And the colored band here is the 95% confidence interval. And as a baseline, I trained a monaural network that just had input from the left ear. So this network wasn't able to make those comparisons to gain the spatial cues. It just had input from one ear. And you'll notice that that network performs a lot worse than both the human participants and the binaural network. So this is pretty interesting because it means that my network is learning to make use of those binaural cues. And here are the results of the source to distortion ratio. So you'll notice that with the binaural network, there's an improvement all the way from 0 to 6 distracting talkers, which means that it's isolating the target talker speech from the distractors a little bit better than just having the raw input audio. The monaural network, on the other hand, only shows improvement when there are no distracting talkers. So this means that it's learning to be able to undo that head-related transfer function, but it's not learning how to separate two talkers' voices from each other. So it's a really cool result. And even though that result isn't directly related to healthcare robotics, it'll definitely have a lot of applications for these medical robotics. So having assistive surgical robots that can focus on speech coming from the direction of the surgeon or scrub nurse, and having these delivery robots that are operating in potentially noisy environments, having all these devices able to better understand what people are saying is really going to make all these auditory interfaces possible. Um, so with that, I'll hand it over to Sylvain. Sylvain is a master's student in our lab, and his area of research is robotics and auditory perception as well. And he'll be sharing on a delivery robot project that we did.
Hello, everyone. I'm Sylvain. I'm here to present the project that resulted in a paper which was accepted in Frontiers AI and Robotic. So everybody knows how the current pandemic situation has impacted the world around us. We've had to distance, lock down, and isolate, which has added a great level of difficulty and stress on many people. One group of people that's mainly been affected by this is our aging population in assistive living facilities. They've experienced the danger of COVID in harsher way, and they were affected by isolation due to their nature of being more susceptible and at higher risk of contamination. So we decided to do something to help residents feel less disconnected and isolated from their loved ones. And we built an end-to-end robotic system that is controlled entirely by speech, that can sanitize itself, and that deliver packages from visitor to resident in nursing homes. So the benefits of robotics in healthcare scenario is tremendous. Robot, for one, cannot transmit respiratory viruses, so it's a natural choice to go with. In order to break the transmission chain, we can't have people being in direct physical contact with the robot. And to make it truly autonomous, it must be able to understand the intention of its user. Not to mention the ease and the learning curve when people can directly speak to a system and it understands them. So our first objective was that we wanted to help residents feel less isolated and disconnected from their loved ones. And the second objective we had was to build this end-to-end robotic system that is totally hands-free. Uh, some technical challenges that we faced was the language barrier, since not everybody speak in similar ways, and there is some misunderstanding from the speech recognition system. And now with some restriction, people have to wear mask, which makes it sometimes difficult to understand. Um, Here's a scenario we kind of envisioned when we built the system is that grandma or grandpa feels lonely and they miss you. You can't really visit them. You don't want to put them at risk. So you decide to cheer them up. You put together a small package with their favorite peppermint candy and a card, and you head over to the living facility where they are. You get greeted by this robot, and you simply place the package on top of the robot and tell it to deliver it to your relative. So now the robot goes on and makes their life a little bit easier and they are happier. So all we did was a replica system basically to have a proof of principle. And to do that, we used the following equipment to validate our idea. We had a TurtleBot 2 with a Kobuki mobile base, which has some optical detection sensor. It comes with an Acer laptop that ran the robotic operating system. For the navigation and mapping, we used the Orbic Astra, and for the recognition system, we had the Raspberry Pi 3, and we extracted the microphone from a Logitech webcam. So here's an example of the setup we had. On the right, you can see the starting point. The robot gets the package, heads, cleans itself, and then over to the destination. For the speech recognition system, we used Mozilla Deep Speech, and we tested it against Gaudi Vosk. We had an intent parser and a simple text-to-speech software for the confirmation between the robot and the human. In our project, we used a state machine. Basically, we just wanted to ensure that the robot was continuously in a finite state at any given time. And if there was any issues, it would jump to its default state and ask for clarification. So in summary, the package is placed on the robot. It gets the command where it's supposed to head with that. It confirms that it got the right command, extract the coordinates of the location from its database, heads over to cleans itself, and heads to the resident's place. Once it's there, it confirms with the resident that they picked up the package and heads back home. So here we can see our first evaluation system. We had two conditions where we tested with mask and without mask. And the interesting aspect here is that for Vosk, it had 1.5% accuracy in incorrect answers compared to deep speech. And next, we've tested with 13 participants. On the x-axis, you can see again deep speech with mask and without mask against Vosk. And the other condition we tested was English as first language against English as second language. Now, the interesting part in here was that both systems performed the same way when English was the first language. And it didn't perform as well when English was not the first language and people were wearing masks, but Vosk still did better. So yeah, to conclude, we've built this end-to-end robotic system that is controlled entirely by speech. And you can find a full demo at tatalab.ca/demos and the link for our paper. Up next is Chris. Chris is a master's student in our lab, and he works on speech perception in AI. He'll be talking about audio AI for rehabilitation robotics.
Thank you for the introduction, Sylvain. So my name is Chris Perlette, and I'll be giving a brief overview of audio AI applications in rehabilitation. And I'll specifically be focusing on the use case of the Indigo exoskeleton that is being used in Maddie's lab and developed by Mojtaba. So I'd like to specify that this is a collaboration between Maddie's lab, our lab, and Reverb Robotics. You'll hear more about them in a bit. And this is a new project, so what I'm discussing is our motivations and objectives. It's not necessarily full results yet. So an important thing about using any form of AI in a project is you have to consider both the system itself, the engineer or creator of that system, as well as the people who will be eventually using it. So to that end, Lukas talked about how robots should look to understand us. We shouldn't have to understand robots. So by including audio AI, we're introducing the most natural version of our communication to them, in addition to the physical human-robot interactions. This is very important because in the instance of the Indigo skeleton, it's initially actuated with physical inputs on sensors. So if a user isn't actually strong enough yet to activate those physical inputs, you can use the auditory commands to go about actuating the skeleton. And then from there, it also adds context awareness. So if you're standing up and using this exoskeleton and you want to sit down or you want to crouch, The initial inputs into the skeleton are going to be very similar for those two, but the final pose and balance points are completely different. So by simply being able to say crouch or sit, you can avoid the issue of potentially falling over as you change your balance point to something that the robot isn't expecting. This also simplifies the training process because, as previously stated, it's much more natural to say sit, crouch, or stand, or walk than it is to say give the user a controller to push a button to actuate those actions. And then you also get the benefit of multi-user input. So during training, you can have both the trainer and the trainee say these commands and have them be very quickly used by the robot. Past that, you get fail-safes. Anybody who has worked on a robot knows how much of a godsend it can be to simply be able to say stop and have the robot stop moving and return to a known safe position. This makes it safer for the system and the end user. And finally, these systems are highly portable. They're small, they can be wireless, and ultimately, it's just they're very nice to integrate into your robotic system. I have a nice little image of the system that Reverb Robotics is developing. As you can tell, it's quite small. So that's just a quick overview of audio AI as a rehabilitation option. And I'd like to thank the people on the screen as well as the organizations for helping make this research possible.